Good morning guys and welcome to Mind Your Math. Today we are going to learn a new chapter which is squares and square roots. Now this is actually a very easy chapter other than the fact that there are a few calculations in this chapter, a few properties of squares and square roots. Maybe the lesson might take a little long to explain because it is a new concept for you guys, but then trust me, this is an easy chapter and it is a scoring chapter also. So let us start with the chapter. Now, if you have got any doubts regarding the contents or the concept that I am explaining in this particular video, you can mail me for doubts in the mail ID given below in the description box. Now, let us start with the chapter. First, let us get to the definition or the basic idea of what a square number is and what a square root is. Now, let me start with the word perfect square. Now, any square number is also called as a perfect square. So, we use them, interchangeably. If somebody says this number is a perfect square, somebody says this is a square number. So, both means the same thing. Now, let us see what a square is. We have got natural numbers, we have got integers, we have got fractions. We have already studied a few number systems. So, let us take a number 2. Okay. We are multiplying again with the same number. Now I can represent in exponential form as 2 square. What is the answer? It's a 4. Okay. A number when squared itself or when multiplied by itself will give us another number which is called as a square of the first number or the perfect square. We can call it as a perfect square. Okay. If I have a number 3, if I am squaring the number, it basically means I am multiplying the number with itself. I will be getting a 9. So I can say that 9 is a square of 3, or I can say 9 is a perfect square. Okay. Take the number 8. Can you think of an integer or a natural number which will give 8 when multiplied with itself? You know that there is no such number which will give me 8 when I am multiplying the number with itself. Therefore, I can say confidently that 8 is not a perfect square or 8 is not a square. Okay. So, from this we understand that in the number system, there are numbers which are squares and where there are numbers which are not squares. Okay. Now, 4 is a perfect square. 4 is obtained by multiplying 2 with its own, which means 2 with a 2. So, I can say that 2 is a square root of 4. So, this is a square and this is a square root. This is a square and this is the square root. If I have a number 16, I am multiplying 16 with itself, I get a 256. So, I can say 16 is a square root of 256 or 256 is a square of 16. So now I hope you have understood the basic concept of what a square is and what a square root is. If I have a number n, any number n, when I am multiplying n with itself, I get n square. This n square is called as the square of n and n is a square root of n square. Okay. If I have a number 25, which number will give me 25 when multiplied with itself? You know the answer is 5. So I can say that 25 is the square of 5, or I can say 5 is the square root of 25. Okay. Now, the symbol for square root is this. The number comes here. So I write, it means the square root of 25 is 5 and square root we synonymously say as root also. So we say the root of 25 is a 5 or the square root of 25 is a 5. Okay. Now, minus 5 into minus 5 also will give me 25. So now the question arises, which one exactly do we write for the examination? Now, in the examination or whenever somebody asks you, what is the square root of 25? You need to understand that 25 has got 2 square roots. One is a plus 5 and other is a minus 5, because even minus 5 into minus 5 will give me plus 25. Okay. So, in the question, if it is specifically mentioned that Write the natural number which is a square root of 25. You know that you should be writing only 5 because minus 5 is not a natural number, it's an integer. So from this, the first point we learned is that any number or any perfect square can have two square roots. One is a plus number and the other one is a minus number. Okay? Till now, I was talking only about the square root or the root of positive numbers. Now, what about negative numbers? When I'm talking about square root, I was talking about negative numbers also. So, why can't I talk about negative squares? Is there a number minus 25 or a minus 36 or a minus 4 ever possible? Because this numerical part I can manage, but what will I do with the minus sign? You know that whenever I am multiplying two numbers with the same sign, I will end up with a plus sign. So I know that minus 4 is never possible because minus 2 into minus 2 will give me plus 4. 2 into minus 2 only will give me minus 4, but then minus 2 and 2, they are not the same number at all. So from this I can understand that there is no perfect square or a square number that is negative, or a negative square number. This is not possible at all because there is no number that will give me a value that will give me minus root 4. So in the system or in the number systems that you have studied so far, square root of negative numbers do not exist. Okay, so that is the second point. Only positive numbers can have square roots. Negative numbers cannot have square roots. The first point was that a positive number can have two square roots, one with a plus sign and other with a minus sign. Right? Now let us move on to the third property. Here you can see that I have written the squares of the first 10 natural numbers. Okay, starting from 1 up to 10, I have written the squares. So, if I am going above 10, I will get 11, 12, 13, etc. But you can see that the last digit remains the same. Okay, now, from this table, the square of 1 ends with a 1. So does the square of 9. Correct? Square of 2 ends with a 4. So does the square of 8. Square of 3 ends with a 9. So does the square of 7. 4 into 4 is 16. 6 into 6 is 36. The last digit is 6. 5 into 5 is 25. And 10 into 10 is 100. Now, look at the last digit of all these numbers. This last digit comes from multiplying these digits. Correct? So, if I am taking 11 into 11, I can immediately say what is the last digit of the number that is going to come here. It will be 1 into 1. Similarly, 12 into 12, the last digit will be 4. 13 into 13, the last digit will be given by 3 into 3, 9, which is a 169 over here. So, you know that this pattern is going to repeat because the last digit multiplication will always remain the same. Now, all these are perfect squares. 1, 4, 9, 16, 25, 36, all these are perfect squares. What is a digit that is not appearing in the last digit of any of these numbers? 2 is not there. 3 is not there. 7 is not there. Then which number is not there? 8 is not there. Okay. The remaining all the digits are appearing in the square of these numbers. Now, if I have a number 248, if somebody asks me, is this a perfect square? I can say that it is not, because the last digit of 8 will not come in the square of any number. Look at the pattern. 347. You can immediately say it is not a perfect square because 7 is not coming in any of these digits, ending digits. So I can say 347 is not a perfect square. Now, if somebody asks you, what is the last digit of 23 square? You can immediately say that it is 9. Okay. What is the last digit of 16 square? You can say it is 6 into 6, 36, so 6. So the last digit will be 6. So 19 square, the last digit is going to be 1 because it comes from 9 into 9. So you'll be writing 1, 8 goes as a carryover. Clear? So if a number is ending with these digits, you can immediately say without any verification that it is not a perfect square at all. That is our third point. Only the numbers ending with these digits have the probability of being a square. The remaining numbers which are ending with a 2, 3, 7 or 8 will never be a perfect square. Okay, now if I say 9, it is a perfect square. What about 19? Just because it is ending with an ion, it is not a perfect square, but it has a chance of being a perfect square if there were other digits over here. But in this case, if 8 is the last digit of any number, there is no chance, whatever be the digits over here, there is no chance that it will be a perfect square. Clear? Out of these numbers, without calculation, how many of these numbers can be called as non-perfect squares, which means which is not a square number? Ending with 7, not a square number. Ending with 3, not a square number. Ending with 8, not a square number. Ending with 9, maybe a square number. 222, no way it can be a square number. 781, ending with a 1, there is a chance that it can be a perfect square. Okay, so from the last digit, it is always possible to say whether a number can be a square number or not. Certain numbers we can outright say that no way this is going to be a perfect square. Okay, what would be the last digit of the squares of these numbers is what we need to know. Okay, 123 square is 123 into 123. The last digit would be a 9. 81 into 81, the last digit would be a 1. 77 into 77, the last digit would be a 9. 7 sevens are 49, 9. 109 into 109 would last digit would be a 1. 9 nines are 81 ending with 1. 85 into 85, it is obviously a 5. Okay, so now I hope you are clear with the third concept, which is finding out the digits and identifying whether the number can be a perfect square or not. Okay, now we move on to the fourth concept. Okay, we have got even numbers and we have got odd numbers. 4 is an even number, 5 is an odd number. Okay, now the square of an even number, will it always be an even number? And the square of an odd number, will it be always an odd number? Now, we will again look at the pattern of the squares of natural numbers and we will take a call on whether an even number square will always be an even number and an odd number square will always be an odd number. Now, what are the odd numbers? 1, 3, 5, 7, 9. Okay, all the remaining numbers in the number system are going to end with these digits, so we call them as odd numbers, right? Now we are only bothered about the ending digit to decide whether a number is even or odd. We are only bothered about the ending digit. 1 into 1 will always give me a 1. 3 will always give me a 9. 5 7 sevens always end with a 49. 9 nines always end with a 1. So any number ending with a 1, when I am squaring it, will always end with a 1. Any number ending with a 3, for example, a 43. 43 into 43 will always end with a 9. 5, I don't really have to say. 7, any number ending with a 7 when squared will always end with a 9 because 7 sevens are 49. This 4 gets carried off here somewhere. Any number ending with an 9 will always end with a 1. So I can say that the squares of odd numbers always end with odd numbers. So the square of an odd number will always be an odd number. Now what about even numbers? So what are the even numbers? We had the even numbers are 2, 4, 6, 8 and 10. Okay. Square of 2 is always a 4. Square of 4 will end with a 16, which the last digit is a 6. The square of 6 ends with a 36, so last digit is a 6. In the case of 8, it's a 64 ending with a 4 and this is a 0. So you can see that the squares of even numbers always end with even numbers. So the square of even numbers are always even numbers. So whenever we are squaring an odd number, we get an odd number, and whenever we are squaring an even number, we get an even number. Okay? Now we have the fifth concept. The first natural number ending with a 0 is 10. The square of 10 is 100. The next one is 100. Okay. The remaining middle numbers ending I am not taking because they only have one zeros. Our consideration over here is a number of zeros in the number. Okay. Now the next one is 1000 multiplied with 1000 will give me, and the pattern goes on and on. What can you see from here? Look at these numbers. The answers. These are our squares. All these squares have got even number of zeros. Correct? If I have a number 1000, which number when multiplied by itself will give me 3 zeros? There is no way that is possible because any number we are taking, suppose it is 10, one more zero has to be added, the zeros has to come in pairs. Okay, so in the case of 1000, there is no number that will give me this value when multiplied by itself. So in order to make it a perfect square, I need to have one more zero over here. Then I can say that 100 is the square root of this number. So that is our next point. The number of zeros will always happen in even numbers or in pairs. There is no way an odd number of zeros will end up as a perfect square. Okay? Suppose you are having a number 5000. Now somebody is asking you, is it a perfect square? You look, the ending digit is 0. So there is a possibility. But you see the number of zeros over here, 3. There is no way 5000 is a perfect square. Okay? Now we have the sixth property of square numbers. Okay. Now this particular property, for ease of remembering, I call it as the haunting by 3 and 4. Okay. Now there is no particular term like haunting by 3 and 4, so that it is easier for me to remember as well as for my students to remember. I use that particular term. So when I say that, they immediately remember this particular property. Now, if you have a square number, suppose you have a number, let us say 36, which we know is a perfect square. When I am dividing 36 by 3, you know that it is completely divisible, 12. Right? Let us take another square number, which is 25. If I am dividing by 20, if I am dividing by 3, what do I get? I get 8 as the quotient and 1 as the remainder. Okay. Any square number, when I am dividing by 3, it is either divisible completely or leaves a remainder of 1. Same with 4 also. Whenever I am dividing a perfect square by 4, it is either completely divisible by 4 or leaves a remainder of 1. Okay. Now, any number that is divisible by 4 or leaves a remainder of 1 is not a perfect square. Or any number that is divisible by 3 or leaves a remainder of 1 is not a perfect square. It is only one way, that a perfect square is completely divisible by 3 and leaves a remainder of 1, or leaves a remainder of 1, is completely divisible by 4 or leaves a remainder of 1. So if somebody gives you a number and then ask you to prove if it is, or ask you if it is a perfect square or not, or if it has a chance of being a perfect square or not, you can divide by 3 and see whether it is properly divisible or leaves the remainder of 1. If neither of this happens, you can confidently say this is not a perfect square at all. But if it is getting divided by 3 or it is leaving a remainder of 1, don't say it is a perfect square. It has a chance of being a perfect square. Okay? Now, suppose somebody is giving you the number 35. Okay, just as an example. and asking you whether this is a perfect square or not. No, you some way in some world you don't know whether it's a perfect square or not. So you first look at the last digit 5. So there is a chance that it is a perfect square. Now they are telling you you cannot find the square root or try to find the square root. You just have to tell whether it is a perfect square or whether it can be a perfect square. So you divide by 3. So when you are dividing by 3, what do you get? So you will be getting 11. Leaving a remainder of 2, you can confidently say, no way this is going to be a perfect square. Okay, because it is leaving a remainder of 2 and not a remainder of 1. You have this number 39654 and 30. Somebody is asking you, is it a perfect square? Do not try to find the square root. Just look at the number and say whether it is a perfect square or not. You can immediately say it is not a perfect square looking at the number of zeros. Correct? There are only 3 zeros. There is no way this is going to be a perfect square. Suppose a person takes out 1 0 over here. This has a chance to be a perfect square. So now I will divide by 3 and see. So when I am dividing by 3, I will get I will get 1321800, which means that there is no remainder. The number is completely divisible by 3. So what will I say? This number has a chance of being a perfect square, but unless I actually find it out, I am not sure whether it is a perfect square or not, but it definitely has a chance. That's a maximum you can say. Okay, let us take another number 348349. Okay, now the last digit is 9. It can be a perfect square. Let us divide by 4 this time and see. Okay, so when I am dividing by 4, 83499, I am dividing by 4. 4 2s are 8, 3. Fours are 28, 1, 9. Correct? 3 is the remainder. I can confidently say this number in no way is a perfect square. Okay, so I hope you are understanding what I am trying to convey. If a number is divisible by 3 or 4 or leaves a remainder of 1, it has a chance of being a perfect square. If not, it will never be a perfect square. Okay, we move on to the next property. This is a very important one. Suppose you have a natural number represented as n. It can be any natural number from 1 up to infinity, any value. If you are representing a natural number as n, what is the consecutive natural number? Next natural number, it will be n plus 1. So if my first natural number is 3, the next natural number is 3 plus 1, 4. Okay. Now, I am squaring the second natural number and subtracting from the square of the first natural number. Okay. This is of the form a square minus b square. This is equal to a plus b into a minus b. Correct? Sorry. My bad. Minus b. So what do I get over here? I will get n plus 1 plus n. This becomes n and n get cancelled into 1. This is basically n plus 1 plus n, which is basically 2n plus 1. But I am not going to write it in that way. It is n plus 1 plus 1. So what do you understand from this? The difference between the squares of successive natural numbers is equal to their sum. If I have a number 30 square minus 29 square, where the value of n is 29 and n plus 1 is 30. Clear? If somebody is asking you to find the value of this, you don't need to particularly find what is 30 square and what is 29 square. You just need to add them. N plus 1 is 30 and n is 29, giving us 59. See, it's very easy to find this particular value. It is especially useful when we are dealing with huge values. Suppose you need to find something like 2333 square minus 2332 square. So what is our value of n? This is our n and this is our n plus 1. So it is the difference between successive squares. So what is this equal to? It is equal to n plus 1 plus n, which is 2333 plus 2332. 4665. See, if we actually sat down to find the square of this and the square of this and then subtract it, you know how difficult it would have been. So this particular property is very important because it gives you the difference between the squares of two consecutive natural numbers. Okay, so I hope you are very clear with this. Let us do one or two sums. Already we have done, but let us do two more of these sums and see how we can apply this particular formula. Find the value of 1010 square minus 1009 square. So basically the remaining question will be by using the relevant property. Now in the first sum, what is the value of n? 1009 and n plus 1 is equal to 1010. Okay. Now it is the difference between successive squares which is equal to n plus 1 plus n, which is 1009 plus 1010. 2090. Okay, you know, it's a straightforward sum, direct application of the property. Now let us look at the second sum. 100 square plus 200 square plus 300 square minus 99 square minus 199 square minus 299 square. So when we first look at it, it looks kind of little complicated because the terms are not segregated properly. So it is our job to segregate the terms. So 100 square minus 99 square, one part, plus 200 square minus 199 square plus 300 square minus 299 square. Now let us see whether we can apply the property. In this case, this is n plus 1 and this is n. Okay. Here this is n plus 1 and this is n, and here this is n plus 1 and this is n. The value of this is n plus 1 plus n, which is 100 plus 99 plus 200 plus 199 plus 300 plus 299. We just have to add all the terms. So we need to find the final value. You will be getting the final value as 1197. Okay. So I hope you are clear with the application of this particular property. This is a very important one because it can be used in a in multiple kinds of sums. They can just mash up all the terms and then give you, where your job is to segregate and then apply the property. Okay. So now can I move on to the next one? Let us have a look at the next property. You have a natural number n. The next natural number is represented as n plus 1. We just saw what happens. Okay, we know that this value is given by n plus 1 plus n. Now, between the squares of two natural numbers, how many numbers are there? Which means that if this number is 25 and this number is 26, how many numbers are there in between these two numbers? They are not squares, right? These are the two consecutive squares. So in between these two numbers, there are no square numbers anymore. So how many non-perfect square numbers are there in between 26 square minus 25, or between 26 square and 25 square? So this particular property is what we are going to learn now. So n plus 1 the whole square minus n square, the value is n plus 1 plus n, which is 2n plus 1. Correct. So in between the squares of two consecutive numbers, 2n numbers are there. Let us see how this is happening. Let us see how many numbers are there between 1 and 10. 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 8 numbers. What is the difference between the first and the last number? 10 minus 1, 9. The difference minus 1 will give me the number of numbers in between two numbers. Correct? So, in between n plus 1 square and n square, the number of numbers will be the difference between them minus 1. The difference between them is given by this formula. Minus 1 will give me 2. Clear? Between the first number and the second number, how many numbers are there is what we need to find. In order to find that, we need to subtract these two numbers. When we are subtracting, we are getting this. I have to subtract 1 from this difference in order to find the exact number of numbers between these two numbers, which is 2n plus 1 minus 1, which is 2n. Okay? How many non-square numbers are there between 26 square and 25 square? So between 25 square and 26 square, all the numbers are non-square numbers anyways, because 25 square is the first square number here, and after that immediately it is 26 square. So in between them, whichever numbers are happening, they have to be non-square numbers. Now, you know that 26 and 25 are numbers that can be represented by n and n plus 1. You know that between n plus 1 the whole square and n square, we have got 2n numbers. Here, what is the value of n? N is 25, n square is 25 square, and n plus 1 the whole square becomes 25 plus 1, which is 26 square. So the value of n is 25. So how many numbers are there? 2 into 25, 50 numbers. So in order to find the number of numbers in between two consecutive square numbers, we need to use this particular formula. Okay? Now, let us have a look at this particular pattern. 1 square will give me 1, which is the first odd number. 2 square is 4, which is basically 1 plus 3. It is basically the sum of the first two odd numbers. When I am calculating 3 square, I am getting 9, which is the sum of the first 3 odd numbers. So automatically, when I am asking you what is 4 square, it is the sum of the first 4 odd numbers. Okay, be very clear. It is only odd numbers, not the first 4 natural numbers, first 4 odd numbers. 10 square, 100. When you add the first 10 odd numbers, you will end up with 100. So my 10 square is the sum of the first 10 odd numbers. So following this pattern, if n is any natural number, what is n square? N square will give me the sum of the first n odd numbers. Okay, so if somebody is asking you to find the sum of the first 100 odd numbers, you don't have to add them, you just have to find the value of 100 square. So basically, n square or n into n will give me the value which is equal to the sum of the first n odd numbers. So just let us apply this property to a sum so that you get a better understanding of this property. Find the sum of the first 50 odd numbers. So they are basically asking us to find 1 plus 3 plus 5 up to 50 odd numbers. So not plus 50, 50 odd numbers. So we know that the sum of the first n natural or n odd numbers is n square. So the sum of the first 50 odd numbers should be 50 square, which is 2500. So without adding individually each of the odd numbers, we can actually find the sum very easily. Now the second one, find the difference between the sum of the first 75 odd numbers and the first 40 odd numbers. So the sum of the first 75 odd numbers is given by 75 square. Sum of the first 40 odd numbers is given by 40 square. Okay. Now let us see what we are getting. So you know that what is 75 square? 75 square is basically 5625. So I hope you know how to multiply numbers ending with a 5 very easily by using the basic technique. For example, if it is 75 square, which is basically, whenever you need to find out the square of numbers ending with a 5, for example, 75 square, 65 square, 55 square, etc. Instead of actually doing the proper multiplication, what you can do is that 75 square is basically 75 into 75. The last two digits will give you a 25. Now, add 1 to the 7, which makes it 8. 8 into 7 is 56. This is our 75 square. So now, by using this technique, let us find out what 45 square is. 45 square is 45 into 45. The n numbers will give you 25. add 1 to 4, which makes it a 5. 5 into 4 is a 20. 2025. So even without using, the pen or the paper or whatever it is, you can now easily say what is 45 into 45. 5 5s will give you 25. Add 1 to 4, which will give me 5. 5 4s are 20. 2025. Now let us see what is 65 into 65. 5 5s are 25. Add 1 to 6, give me a 7. 7 6 are 42. 4225. Okay. So now let us find out the value of this. 75 square will give me 5625 minus 1600. This is our required answer. Okay. Now that you are clear with all of these properties, let us do a small recap of all the properties before I move on to the next one. So here is a short recap of all the properties that we have done so far. They are not in the order in which we have done. So I have just written it down. But so the first property actually is that there are 2 square roots for every single number. If 4 has got 2 square roots, which is a -2 and a +2. Depending upon the question and the conditions in which the question is asked, you have to choose the appropriate square root. So in some cases, if they're asking you only the square root of 4, you need to write both the square roots, which is -2 as well as +2. Going by the same logic, I can say that the negative numbers do not have any square root. Okay. Now, numbers ending with 2, 3, 7 or 8, we have seen that they can never be perfect squares. Similarly, numbers which are ending with odd number of zeros can also never be perfect squares. Okay. Now, the squares of odd numbers are always odd and the squares of even numbers are always going to be even. Now, the next one is a haunting by 3 and 4. So, we saw that how a number we can identify as a possible square number by dividing by 3 or by 4. So, we can only identify if it can be a perfect square or not. We cannot convincingly say it will be a perfect square. So, if somebody asks you, is this number a perfect square, and you are using this particular property and it turns out to be negative, we can say that this is not a perfect square, or it can be a perfect square. Okay. Now, the difference between n plus 1 the whole square and n square is the sum of the two numbers. Same extension of the same logic. There are 2n numbers between n plus 1 the whole square and n square. Okay. And the sum of the first n odd numbers is n square. So these are the properties that we have done so far. Now we move on to the next property, which is based on the Pythagoras theorem. Now in grade 7, you have already learned what Pythagoras theorem is. It is basically hypotenuse square is equal to base square plus altitude square in a right angle triangle. So now we have 3 numbers, 3, 4 and 5, and hypotenuse. Suppose this is a right angle triangle, this is 5, this is 3 and this is 4. Okay. So you can say that 3 square plus 4 square has to be equal to 5 square, which in this case is true because this is 9 plus 16, which is a 25, which is equal to 5 square. Okay. So this is Pythagoras theorem. Now these 3 numbers, 3, 4 and 5, I can say will make a Pythagorean triplet. Pythagorean triplet are basically 3 natural numbers that will satisfy the Pythagoras theorem when it is applied to the sides of a triangle. So in this case, 5 square is equal to 3 square plus 4 square. So there are many Pythagorean triplets that we know about. Now there is a general formula for the representation of Pythagorean triplet, which is given by 2m, m square minus 1 and m square plus 1. This is a general representation of a Pythagorean triplet or a set of Pythagorean numbers. Now, depending upon the value of m, we can have different sets of Pythagorean triplets. Suppose the value of m is 2. So, you will get the value over here as 2 2s are 4. So, 4 minus 1 3 and 4 plus 1 5. 3 4 5, the one that we explained before. Now, let us take the value of m as a 10. So, what do you get? 10 2s are 20. 100 minus 1, 99, 100 plus 1. So, basically what they say is that 101 square is equal to 10 square plus 99 square. Okay. So, we can substitute different values for m in order to get different triplets. Okay. Now, Since I have told you the general notation for a Pythagorean triplet, let us see whether it is actually satisfying the Pythagoras theorem. In this Pythagorean triplet, this has to be the largest number. So this should be the hypotenuse. I need to show that m square plus 1 the whole square is equal to base square plus altitude square. Okay. Now let us see what are the values we are getting for LHS as well as for RHS. My LHS becomes, I am opening the brackets using a plus b the whole square, a square plus 2ab plus b square. What am I getting in the RHS? 4m square plus m raised to 4 minus 2m square plus 1. So this is basically m raised to 4 plus 2m square plus 1. This and this, okay, gets cancelled to give me 2m square. So I can say that the RHS and the LHS are the same. So this is indeed the general representation of a Pythagorean triplet. Fine. Write the Pythagorean triplet whose one member is 6 and the second question is 18. Now you know this is a general representation of the Pythagorean triplet. Now one member is 6 basically means one of these values is equal to 6. Now let us see which value we can take as 6. Let us try with m square minus 1. If this is equal to 6, you know that m square is 7. M7 is not a perfect square. I cannot find the square root. Okay. Now, same m square plus 1 is equal to 6. I can say m square is 5. Not possible. So, the only value that is left over here is 2m. So, I can say 2m is equal to 6, m is equal to 3. Once I get m is equal to 3, I can find m square minus 1 as 9 minus 1, 8 and m square plus 1 as 9 plus 1, 10. This is my Pythagorean triplet which is 6, 8, 10. Now let us find the Pythagorean triplet where my value 2m is equal to 18. So when I am getting 2m is equal to 18, I get m is equal to 9. So m square minus 1 becomes 80 and m square plus 1 becomes 82. Okay. So my Pythagorean triplet now is 9, 80 and 82. I hope you are clear with this particular concept and how to apply it on the sums. Now that we are done with the basic properties of squares and square roots, or basically squares. So see, we have covered almost all the important properties. So now let us see what are the possible sums that can come regarding those properties. I have taken these sums from the NCERT book. I have picked out a few sums. So let us see how we can do this. These are very easy. What will be the unit digit in the square of the following numbers? 81. The square of 81 is basically 81 into 81. You know that the unit digit is the product of these two. So 81 square will end with a 1. 5, 2, 6, 9, 8. You know that the last digit will be the product of 8 and 8. So it will be ending, it's a 64. It will be ending with a 4. 1, 2, 3, 4. It is basically 1, 2, 3, 4 into 1, 2, 3, 4. The last digit will be the product of 4 and 4, which is a 16. 1 will go as a carryover. So the last digit will be 6. 2, 6, 3, 8, 7. The last digit will be 9. Okay. Now, the following numbers are not perfect squares. Give reasons. 1057. So we know 1057 is not a perfect square. The reason being, a number ending with the digit 7 cannot be a perfect square. Okay, we have already seen why. So that is the reason why 1057 is not a perfect square. The same logic applies to 23453. It is ending with 3. It cannot be a perfect square. 64,000. The reason 64,000 cannot be a perfect square because it has got an odd number of zeros, not an even number of zeros. This number is ending with a 2, so it cannot be a perfect square. Okay. Now the next one. Without adding, find the sum of 1 plus 3 plus 5 plus up to 19. We have seen that the sum of the first n odd numbers will be equal to n square. So this is starting from 1 and it is going in sequence. So I can say that these are the odd numbers from the beginning. So how many odd numbers are over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 odd numbers are there. So we know that the sum of n odd numbers is n square. the sum of 10 odd numbers is equal to 10 square, which is a 100. Right? Now, the last one, I don't think it is visible. Okay, just how many numbers lie between the squares of 12 as well as 13? Squares of 12 as well as 13 is between 144 and 169. How many numbers are there is what we need to find. We already saw that the number of numbers between n and n plus 1 is equal to 2 into n. So here, what is the value of n? The value of n is 12. So 2 into n will give you 24. So there are 24 numbers between the squares of 12 as well as 13. Okay.